let's see. How's that? Can you see that?
Yep, there you go.
All right, perfect. Okay. So then on the 13th, when we come back, this is in terms of lecture type material, we'll be finishing up the Unit 3 stuff. So we sort of get into a special topics, examples, and more practical type applications. And the last homework we have is the Unit 3 homework number 4. And I want to cover that actually in lab with you guys. We have a lot more time in lab because the lab lecture is going to be basically non-existent because not much goes on in the second day of the experiment 10B. So it's going to be a really light lab lecture, and it's a great time to cover that homework. And so we're going to be doing that in lab. As a result, you need to submit it before I go over the answers. So submit it on Canvas by 2 p.m. on Monday. That's the 13th. And it's not expected you're going to get every one of them right. We'll go over together the answers, but it's one of those, it's graded on completion, a lot like the end homework problems in Unit 2. So that'll be in lab. And then also in lab, we'll be doing some more examples and just practice type problems. So Monday in lecture, I'm just going to finish the material, but there won't be any homework that we're going to be covering in lecture because we're pushing it off to lab. Then Wednesday is exam 3, and that's going to be a lab exam, and that's Wednesday the 15th. It's going to be a lab exam. You'll need to have, well, assuming you've used them, models. They're very helpful. And also a calculator because of the polarimetry type questions. Okay, so that will take up time in Wednesday in lab, and then we'll have a brief lab discussion afterwards on 11A. That's not very long. Okay, and that exam 3 is another class is going to be taking it this week, I think, the end of this week. And so I'll have a better idea of the timing of that. They're going to forge ahead and figure that out. See how it goes.
Isn't there like a quiz?
Quiz on the Monday?
There's a quiz that's a lab issue. So that's you'll have on Monday you'll have a lab quiz, and it's just 10 questions, small guy, on stereochem and polarimetry, and it's 40 minutes long. Okay, so we're winding down in the unit, which is kind of nice. All right, so I want to, before we launch into doing some more stuff with SN1, want to kind of go back and recap and talk about the SN2 reaction, and then we're going to talk about what we know about SN1 and extrapolate on that a little bit. So as far as SN2 goes, it is, in terms of the substrate, whoops, TATE, there we go. In terms of the substrate, it is seen in methyl halides, which is, you're unlikely to get one of those. That's kind of boring, but a methyl halide. It is seen in primary alkyl halides, and it's seen in secondary alkyl halides. It is not seen in tertiary alkyl halides. And the reason for that is that they are too hindered. Okay, the nucleophile can't get in on a tertiary. There's another set of molecules it's not seen in, and I'm just going to draw them. Aryl halides, it's a benzene ring, or a halogen on a double bond. Those are planar, and there's no backside attack possible. So in a nutshell, when you're dealing with SN2, methyl, primary, secondary. And oftentimes, like on the problem sheet you guys had, that can really help immediately narrow down what kind of mechanism you're looking at by just looking at the actual substrate. Okay, in terms of the nucleophile with an SN2, get an actual pen, here we go. In terms of the nucleophile, SN2 requires a good nucleophile. And we saw the species that made good nucleophiles last time. These are species that have a large amount of electron density. And where that electron density is not tightly held. So things that are super electronegative generally aren't great nucleophiles. So nucleophiles, a lot of them have negative charges. They're negatively charged, like N3- or HS-. Those tend to be the good ones because they have a lot of electron density, obviously, with that negative charge. You can see nucleophiles, though, that have lone pairs. Not as common for them to be good, though. They tend to be not as good. They're down there in the fair to weak nucleophiles. But we'll see water, for example, just has a lone pair. It's a nucleophile. It's not a good one. Or in alcohol, we can just make it generically ROH. They're nucleophiles. They've got the lone pair. They're not going to be strong because they don't have the negative charge. And then we learned about leaving groups. That's what LG stands for, leaving group. And the leaving group, in order for a reaction to occur, and this applies to SN1, SN2, any of those, you have to have a leaving group. And we saw that good leaving groups are classified as weak bases. And what that really means is that they are stable on their own. They're stable being kicked out. They're things that can stabilize the negative charge. Spread it out. So some things that made a leaving group good were, like, we had an example of I-. That's a pretty good leaving group. It's large and it can spread out that negative charge. Other good leaving groups are things that are resonance stabilized. So we saw a compound that was a sulfonate, and this is stabilized by resonance. So it's something that when it leaves, it's stable. Now, strong bases are not leaving groups. So we will not see OH- leave, H- leave, NH2-, or the basic form of any alcohol. Those aren't leaving groups, and that's because they're strong bases and they aren't very stable on their own. They're very reactive, so they don't leave. What we can do as a trick, though, is turn them into, in a separate reaction, turn them into a good leaving group. And we looked at an example towards the end of lecture where we have OH and we could treat it with HI, for example. And the first thing that happens is the OH won't leave, but we're not going to ask it to. We're going to protonate it. And so now it's OH2 plus, and that is, when it leaves, is water. As a leaving group, it's water. That's a good leaving group because it's a weak base. And then I minus is then able to come and kick it out. So there are tricks that can be employed. You can get a bad leaving group to leave, just not directly. You got to do a little something first to it. And then the last thing that we looked at was the solvent. And I talked about how this was the one that was most frequently disobeyed. So don't use this to make your decision. The solvent for an SN2 is one that will not hydrogen bond to the nucleophile. So you need it polar, but aprotic. So there's no NH, no OH. And because of that, it can't hydrogen bond to the nucleophile because that'll slow down the nucleophile. So polar aprotic solvents, real common one is acetone, dimethylformamide. Take a look at the list that we looked at. Okay, sometimes mixed with water, which is not a great SN2 solvent, but there's a solubility issue as well. Okay. Let's see. Any questions on SN2? All right, let's go. Go ahead.
I had one question. So wait, so SN2 inverts the stereochemistry, but SN1 doesn't, or
That's
does it
yeah.
also? Or,
It can, and well, we'll get into that actually in just a minute. What you see is you see a racemic mixture develop. So some it's inverted and some it's not. And we'll take a look at why that is in just a second. So let's make a note here too. Under SN2, put inversion of stereochem. I forgot to add that. And that's one of the things that you do see. All right, let's do SN1 now. Let's sum up what we know so far. We didn't get too far into it, but we did a little bit. So with SN1, in terms of the substrate, the substrate in an SN1 reaction, in the rate determining step, forms a carbocation. And so the key thing about the substrate is it must make a stable carbocation, or that's not going to happen. So a stabilized carbocation is key. And we talked about carbocations. They were a carbon that had three things on it: trigonal planar, and it had a plus charge, so there's an empty p orbital. And they're, of course, electron poor. And they could be stabilized by a couple of things. They could be stabilized by resonance. So there were some examples. Let's draw one like this. In a ring, I'll put a carbocation, make it a secondary one. I'll put a double bond there. That carbocation could reasonably form because my double bond can move up into that empty p orbital, and I can draw a resonance structure where I have my double bond up top now and the plus down to the side. And the real molecule, of course, is a hybrid. So I have my double bond partially over the whole system, and the plus charge is sort of partially over the whole system too. It's all spread out. So resonance can stabilize your carbocation and make it easier to form. Say you don't have resonance though. There's an order in just carbocations in general that tertiary carbocations are more stable than secondary carbocations, are more stable than primary carbocations, and those are a ton more stable than methyl. You can take a methyl carbocation, switch ink colors, and draw a nice big red X through it. It's not going to happen. Now the reason for this, let's go ahead and let's draw a tertiary one. I have a C, I have my empty p orbital, and I have another C, put H's there, and a C, H is there, a C with its H's here. The attached alkyl groups are electron donors. So attached carbons are electron donors, and it's through a process. It's a little weird. It's hyperconjugation. But it's just where the electron density in the neighboring bonds can kind of spill over and help stabilize that p orbital. So what you need to know in a nutshell about it is attached R groups are electron donors. The more you have, the more R groups, the greater the stabilizing factor. And so that's why tertiary is better than secondary, is better than primary. Methyl hasn't got any, it's not going to form. Then the second factor we were looking at, so I think, am I going AB here? Yep, I am. Second factor was the nucleophile. What's interesting about this, SN1 means that there is one species in the rate determining step. That rate determining step is the formation of the carbocation. And that happens without the nucleophile. There is no nucleophile present in that step. So the nucleophile is not important in SN1. Now that's for kinetics, right? Because we're talking about rate determining step, fastest step, and whatnot. The nucleophile doesn't figure in officially in the rate law. It's not important. However, it's a fact that SN1 reactions are favored by poor nucleophiles. They are most commonly seen when you have a poor nucleophile. Very often water or an alcohol. And the reason for that is that the nucleophile is really slow, right? It's not very reactive. And what that means is it allows time. There's time for the carbocation to form. That's a slow step. It's the rate determining step. And so if you have a nucleophile that's sitting around doing nothing, then the alkyl halide gets more of a chance to ionize, and then the reaction can take off. So when we are looking at SN1s, we are almost exclusively, I guess 90% of the time, going to see them with poor nucleophiles. So let's go ahead and take a look at an example or two of that. And I want to introduce a kind of reaction and then talk about the inversion of stereochemistry and what happens there. So let's say we had let's just do this reaction. I've got, let's make it a secondary. And I'm going to treat it with water. So it's a secondary alkyl halide. A secondary could do SN2. Right, they're a reasonable SN2. They're also kind of a stable carbocation. They could do SN1 as well. So just looking at the substrate, that's not real helpful because it could go either way. I look at water, and water is a weak nucleophile. So what this tells me is that SN2, which requires a good nucleophile, is not likely. So I'm going to cross that off my list. And I'm going to say SN1. So what happens in an SN1 is I'm going to lose the bromine. I'm going to create a secondary carbocation. And then water's the nucleophile, and it comes and attacks with its lone pair electrons. So let's draw what that thing looks like. I have an O, 2 H's, and the oxygen has a plus charge. Now the product is not charged. So if the oxygen has plus charge and it's OH2 plus, what do you think I do to get rid of the positive charge? What do you think the next step is? It's the next and last step.
Deprotonate.
Yep, exactly. You're going to deprotonate. So another water molecule grabs the H, electrons go onto the oxygen, and I have turned this into an OH. So it's a substitution, and the nucleophile was water. Everyone okay with that mechanism? Okay. Okay. This kind of reaction's a little bit weird in that I have my nucleophile as water, and my solvent is water as well. So water had sort of a dual purpose. It was the only thing there, so it was the nucleophile, and it was the liquid that the reaction ran in, so it was the solvent. When your solvent gets incorporated into your molecule, so it's the nucleophile, that reaction has a special name. It's called a solvolysis reaction. Solvolysis. And it's seen with water and alcohols. That's where it's going to pop up. Let's do one that's chiral now. Let's do a carbon. And we'll put, let's put a, I don't know, iodine on there as my leaving group. A methyl, straight up. And an ethyl. And then let's keep it simple. And we'll do an H.
So does that mean that we usually see solvolysis in SN1 reactions?
You'll see solvolysis in an SN1 when the only thing there is solvent. So see, the only thing I had over my arrow was water. That's solvolysis. That's how you can recognize it.
Okay, because aren't like H2O and ROH like weak nucleophiles, so they wouldn't
Right.
really be for SN2s?
They won't do SN2s, no. So you won't see water in doing an SN2 reaction.
Okay,
So SN2s won't do solvolysis.
okay.
Okay, so we have, again, a secondary alkyl halide, and let's do it with, let's do it with a weak nucleophile. Let's do methanol. So an alcohol. Notice there's nothing else there. It's another solvolysis reaction. So what's going to happen is methanol doesn't attack anything because it's not a good nucleophile. So the only thing that can happen is I lose I, and I end up getting a carbocation. Now the carbocation is trigonal planar. So I'm going to have a C, CH3, and then I'll have an ethyl here and an H there. This guy's trigonal planar. It's got a p orbital. I'll just draw the p orbital like that with a plus charge in it. Now here's the interesting thing about the stereochemistry of an SN1. When my nucleophile attacks, and I'm going to draw the nucleophile up here in the middle, just like this. When it goes to attack, it sees a trigonal planar molecule, and it's going to attack the carbon, but the top side of the carbon and the bottom side of the carbon are exactly the same. So in this, it's the different sides, the way I drew it. So the O could attack there 50% of the time, or same thing to it. It could attack there 50% of the time. And since the top and bottom faces are exactly the same, if you like hold your hand out flat and picture a p orbital would be a pencil going through your hand, nucleophile doesn't care if it attacks the top of your hand or the bottom, right? It's the exact same. So you actually end up with a mixture that's 50-50. So I have a C, and I might have my ethyl forward, my H back, and OCH3 attacking from the right. Just as likely to have my methyl up, ethyl push the other way, and OCH3 having attacked from the left. It's 50-50. Those are enantiomers. And so you end up with a 50-50 mixture of enantiomers. You end up getting racemic mixtures. So you can't say that they invert all the time. They do invert half the time, just 50-50. Okay. All right, so I think we can go now, but that sort of summarizes, I'm pretty sure, where we were at. Let me grab my lecture notes real quick, make sure I haven't left any key things off. I think we're ready to go. Where we sort of ended up was looking at the leaving group, and we talked about how the leaving group is a leaving group. You still need a good leaving group. Okay, so we were there. Okay. So both SN1 and SN2 require a good leaving group. So if for SN1, you cannot have leave OH, NH2 minus, OH minus, NH2 minus, RO minus. Same rotten leaving groups in SN2 are rotten leaving groups in SN1. And we would have to do a trick to make it better. That there's no difference there between those two mechanisms. Our last deal now brings us to the solvent. We talked about protic versus aprotic. Aprotic solvents can't hydrogen bond. They're good for SN2 because they won't hydrogen bond to your nucleophile. We don't want anything surrounding our species and slowing them down. For SN1 though, things are different. We need to stabilize the carbocation. If it's not stable, it's not going to form. So it's best if your solvent can even help stabilize it. And when you look at polar protic solvents, they can cluster around it and help stabilize. And that's this picture right here. You see some alcohol molecules. And remember, with polar protic solvents like alcohols, the OH bond's really polar. And so the oxygen has a very large delta minus on it. And that delta minus can cluster around our carbocation, which is wanting electron density. And they can cluster around it and help to stabilize it. Okay, this is a picture of that happening. So this is in the SN1 situation. This is good. Here's a polar protic solvent in the SN2 situation. It's going to slow down the nucleophile. So in SN2, it's bad. And so what we'll see is we're going to see SN1 reactions a lot of times run in water, alcohols, which we just saw 2 examples of, right? And a lot of times that solvent actually is the nucleophile too. All right. So let's see where we're at. I think we're on to eliminations. You guys have any questions? Okay. I think before we do eliminations, there's a couple slides. Here we go. Just talking about the stereochemistry of the two. And so it's a comparison, which we did sort of a little bit in our summary. SN2 reactions are straight out inversion. SN2, inversion. SN1, mixtures of enantiomers. And those mixtures are usually 50-50. So usually you have a racemic mixture.
Is this
And
the
that's,
page that's like all the way at the end? I'm sorry.
it might be, yeah, I might have pulled it in. Let me see. I'm looking at my packet. I think it is. Well, where is it? Where is it? Where do you guys have it in your packets?
I see it at the end.
I
but-
don't think it's
At
in
the
our
end?
packets.
Isn't it? Okay. What I'll do is I'll put it up. No, it's at the very end. Turn your packet to the very, very end.
Page 22.
Okay, I
Yeah.
see it.
Yeah, I pulled it in because it made better sense there than at the end. Okay, so that just gives a couple examples of what we talked about. And with an SN1, the key thing is the fact that you are going through that planar carbocation. And so top and bottom attack are equally likely. Attack from the top, attack from the bottom, both are likely. There's no particular reason to favor one over the other. All right, so this next problem right here, this is another example of your leaving group being a bad leaving group. We have an OH. It would leave as OH minus, and that's a strong base. So it is not happening. So I'd like you guys to take a second. You do the mechanism of this one on a piece of paper, and then I'll put it up real fast and we'll see how you did. Okay. This mechanism goes through a pretty stable tertiary carbocation. And the trick there was, like we saw earlier, protonating, which is a very common trick, to turn that OH into a good leaving group, and it leaves as water, giving us the carbocation. And then from there on out, the mechanism's easy. The reaction goes pretty smoothly, bromide attacks, and there you are. Okay, now you guys should have as your next slide rearrangements, right?
Yes.
And what I'm going to do, I want to get to elimination, and the rearrangements, I'm going to save that for lab, because I want to spend a fair amount of time. I want to show you ring expansions, all that kind of thing. And so we'll be doing rearrangements in lab and do a ton of examples there. So just kind of hold off on that sheet for a little while. Let's finish this up with looking at the mechanism and the products of the following reactions. So they're substitution reactions. And what we're looking for here are SN1 or SN2 or no reaction. All right, so let's go through this really quickly and see what we come up with. All right, so analyze substrate first, and we'll go down the first column and then down the second column. We'll go like that. First thing I do when I'm looking at this is I look at substrate. I classify it: primary, secondary, tertiary. So first one in the first column, we'll call it A. When you look at that molecule with the iodide, primary, secondary, tertiary.
Primary.
Primary.
Good, primary. What kind of a nucleophile do I have? That's the second thing I look at. It's HS minus. How do you classify that nucleophile?
Good.
Yeah, it's a good nucleophile. So primary substrate, good nucleophile. This is pointing towards what kind of mechanism?
SN2.
Yeah, it's pointed, everything's pointed towards an SN2 mechanism. And when you draw the product, you're going to get, I sort of drew that alkyl group weird. You're going to get an SH. Another thing that points towards an SN2, third thing I look at, solvent, right? The solvent is DMSO, polar aprotic. Polar aprotic solvent. So it's an SN2 mechanism. All right. Take a look at the second one. Spend a few seconds with it and let's see what you think. This one, I've got a secondary substrate. CN, decent nucleophile. DMF. What kind of solvent is DMF? If you look at your sheet, that sheet that lists all the solvents. You guys see it in there? I think it's in one of our slides too. Flip back to the solvent slide, somewhere in here buried. Okay, it's on page 7. DMF is a dimethylformamide. It's polar aprotic. So this is an SN2 reaction. What is OTS? Probably should talk about that. What is OTS? There's silence. Flip back a couple slides to the leaving group. OTS is that guy right there. It's one of those sulfonate anions, and it's a leaving group that is stabilized by resonance. It's a good leaving group. We'll learn more about those when we get to, spelled that wrong, when we get to the alcohols chapter. And so it's a super good leaving group. So it's an SN2. We're going to have inversion. So CN will be going back.
Professor, could you just remind us again why we have the inversion?
Oh, because there's a backside attack.
Oh, okay, yeah, thank you.
Yeah, it's a backside attack. Okay. Now the next one, I'm going to take, let's just do the mechanism. As far as the product goes, I'm going to give it to you, and we're going to do that mechanism in lab when we do rearrangements. But I think you can tell what the mechanism's going to be. You have a good leaving group. Br minus is big, it can delocalize the negative charge. Secondary substrate. Tell me about your nucleophile.
It's a poor nucleophile?
Yeah, it's a weak nucleophile, exactly. So we know it's not SN2. We're going to be going SN1 through a carbocation. And I'm going to give you the product. And as I said, when we get to lab and start doing rearrangements, we'll totally do the mechanism and you'll see why it does this. But it rearranges. And so you get a rearrangement. And that is something that is only going to be seen with SN1 and E1 type mechanisms. And we'll do that mechanism next time that we meet up. Okay. The next one in the list. It's secondary. What kind of nucleophile? CN minus? You consult your nucleophile
Good.
list. It's a good nucleophile. Okay. DMF is a good SN2 solvent. So I've got a good nucleophile, good SN2 solvent, secondary substrate, which can do SN2. What's my mechanism?
SN2.
Everything is set up for it to be, but I'm going to give you a hint. No reaction. What killed it?
Leaving group.
It wasn't the
The
solvent.
OH.
The OH. Yep. What's the problem with the OH?
It's really stable and
Bad
I don't
leaving.
know.
It's a, it's a strong base, and so it's a terrible leaving group. It won't leave. So even though I have the world's perfect setup for it, it won't leave. And so if it's not leaving, nothing's happening. All right. The top one here in the second column. Tertiary substrate. Good leaving group. I minus, good leaving group. Methanol, we saw that before in the earlier problem, poor nucleophile. If this thing's tertiary and I got a nucleophile that's not a good nucleophile, what's my mechanism?
SN1.
It's an SN1. Yep, absolutely. And the product is going to be OCH3. This is an example of a solvolysis mechanism. The solvent is the nucleophile. Okay.
Wasn't
This
the
next
third one also solvolysis?
which third one is this?
The The
Oh, on the first column, yes, it was. It was solvolysis. Because the solvent was the nucleophile. Yep. That was solvolysis plus a rearrangement. All right. Next one in the column, secondary substrate. This tosylate is that resonant stabilized leaving group. Good leaving group. Now I've got water, which we know is a weak nucleophile. And there's also an alcohol. That's a little weird, but I've got an alcohol there too. What mechanism would you suspect based on what we're seeing so far?
The SN1.
SN1, yeah. I've got a substrate that could do either. So the substrate, the leaving group, that's not helping me. I look at my nucleophile, water, it's a weak nucleophile. Now the alcohol is an added little twist bonus to this because we've seen where alcohols can be the nucleophile as well. And so with this one, a reasonable question is, well, which one's the nucleophile? And what's going to be probably helpful to eliminate the bottom one and call it the solvent is it's more hindered. It's going to have a hard time because it's hindered. It's going to be not such a great nucleophile. It's going to be a worse one than water, which isn't hindered. And so water's going to have an easier time attacking. If it's SN1, we're going to have OH going back, but you get a mixture of enantiomers, get OH going forward too. We get both. All right. Yeah, go ahead.
About the third one that we did, that has rearrangement also. Does that also
Yes.
get a 50% mixture as well? Or no?
That carbon, it would attack from both the front and the back side, but that carbon that it's on is not chiral.
Oh, okay. Oh, that's
And so
right.
you would, yeah, you wouldn't be able to tell. It would. I mean, there's attack from the front and the back, but it doesn't matter. You wouldn't be able to tell that. Okay, this next one, secondary substrate. Good leaving group. CH3CN, that's on my list of solvents. If I go and look it up, is it even on there? CH3CN, they don't give that one to you. It's called acetonitrile. It's aprotic. I don't see, and the reason I know that is there's no OH, right? So it can't hydrogen bond. So it's aprotic solvent. My nucleophile, N3 minus. Tell me about N3 minus.
not a good one.
Well, let's see. I'm looking for my nucleophile list right now.
Yeah, it says it's a weak base on the list.
Yeah, it's a weak base. How is it as a nucleophile? Decent, bad?
Good.
It says, yeah, it says good. It's in the
It
good
says good
column.
nucleophile, yeah. Yeah, it's a weak base, but it's a pretty good nucleophile. So I've got secondary, good leaving group, aprotic solvent, good nucleophile. What's my mechanism?
SN2.
It's SN2. Yep, everything points to SN2. And it's going to have an inversion of stereochemistry. So N3. Ooh, let me straighten that up. I started to write a CN. N3 is going to be going back. All right. Try the next one. Tell me what you get.
Wouldn't it be no reaction?
Haha, good for you. What What made you decide that?
OH.
The two alcohols.
Yeah, the OH is not a leaving group. Unless I do something to it, and I've got no acid there to protonate it, so I'm done. It's no reaction. Okay, so we've tackled everything but rearrangements, and we'll do rearrangements with SN1 reactions in lab. So we're going to move on now so you can recognize E1, E2. I want to get to those really quickly. This discussion, a lot of the things that we just learned are going to be applicable, so it's going to go a little bit smoother. So just elimination reactions in general will either be E2 or E1. They both have the same outcome, but the mechanism to get there is a little bit different. So both of them are going to have a hydrogen and a leaving group. So we have a hydrogen and a leaving group, and we're going to be removing those. So there's going to be something functioning as a base in the reaction. We'll be taking the hydrogen in the leaving group, getting rid of them, and forming where the H in the leaving group were, those two atoms forming a double bond. So elimination reactions, no matter the mechanism, produce pi bonds. And we're losing a hydrogen and a halogen. So their name sort of indicates that. A D means leaving, getting rid of, hydrohalogen, or hydrohydrogen, and halogen. So they're a dehydrohalogenation, which means you're losing HX. Now, there are two possible mechanisms. The first mechanism is the one here on the top of your slide, and that is a mechanism that is an E2 mechanism. In this slide, I don't know if I rearranged your slides. Is that the next one for you guys? I'm working off a packet that's a semester or two old. You have this slide. If it's not the next immediate one, flip over like one page.
Yeah, it's not the next one.
Yeah,
Yeah,
it's on
flip-
page 15.
Yeah, flip over a page. So in an E2 mechanism, you have everything occurring kind of in one step, very similar to SN2. So we are going to have the base, remove the hydrogen, and then the electrons form the double bond, and the leaving group gets kicked out. And all that happens in one step. So the mechanism sort of showing that. Here's our base. It's grabbing the hydrogen. So that's the deprotonation. Electrons between that were the carbon-hydrogen bond, they move up to form the double bond, which then shoves out the leaving group. There is one transition state, and then you get your product. So let's zoom down and look at the rate law for it real fast. Look at the potential energy diagram. It looks very SN2-like. I have my base, my substrate, my transition state, where I am doing my deprotonation right here. So the base grabs the H right there. And then the leaving group is getting pushed out right here. And as part of that process, I'm starting to form the C double bond C. And so you can see it occurs just in one step. Very SN2-like. Okay, some particulars about it. And we'll take a look at these in a little more detail in the next few slides. One step, or what's called concerted, means it happens all together. Single transition state. And another thing we're going to see, base attacks the hydrogen. We saw that the hydrogen and the leaving group have to be 180 degrees apart from each other. And we're going to take a look at why that is in a slide or two. But they have to have an arrangement that looks like this. Here's a carbon, here's carbon. The hydrogen has to be here, and the leaving group has to be there, 180 degrees away from each other. And that's called anti-periplanar. They're anti, and they're in the same plane. So that's E2. This next one's E1. And with what you know about SN1, E1 occurs through a carbocation. So we're looking at a two-stepper here. So in E1, we form a carbocation first. The leaving group leaves. We have a carbocation. It sort of looks a little weird here. There's our carbocation. And then in the second step, the base deprotonates and we form the double bond. So it ties in really nicely with an SN1 in that you go through this carbocation intermediate, but instead of the nucleophile attacking, we have a base that just deprotonates. And if you look at its rate law, you can see there are two steps. This first step, we form the carbocation. And in the second step, we deprotonate. And we form C double bond C. All right, so let's go ahead and start talking about some of the particulars of these reactions. So pretty clearly with an elimination, we need a base. And both of them need a base. So we need a base in both E2 and E1. And what we're going to see is that when you're doing an E2, strong bases favor E2 reactions. So we're going to see E2 reactions with bases that are down in this lower list down here. OH minus, CH3O minus, H2N minus, and like R2N. So amines that have been deprotonated. Those are the bases that will give us E2 reactions. And this just, all this wording here, we've seen that before, just ways of predicting base strength on the periodic table. So you can go over that and just refresh it on your own. But the take home thing, memorize these. Those are the E2 strong bases.
And the weak bases then are for just E1?
Weak bases are for E1, exactly. So we're going to see E1 when you look at the weak bases that it's seen with. A lot of the times, water and alcohols is where we're going to see E1 reactions. Okay, so it sort of tracks along, like SN2 needs strong nucleophiles, E2 needs strong bases. All right, let's take a look at the mechanism. So for the E2 mechanism, we talked about how the halogen and the proton, the hydrogen, have to be 180 degrees apart. In other words, anti. They have to be anti to each other. And this is shown in a Newman so that you can see it clearly, and then we'll show you with some orbitals. So here's the Newman. your molecule has to rotate so that the hydrogen and the halogen that's leaving are anti to one another. And that anti-coplanar arrangement, it shows how the orbitals all line up here in this second picture. And if you take a look at it, it allows for a really smooth flow of electrons in between orbitals. And so the base grabs the hydrogen, electrons flow from one orbital to another, and then they flow out to kick out the halogen. And so it gets the orbitals lined up correctly. And it also, sort of as an added bonus, it gets everything staggered. It's a staggered conformation, which is lower energy. But you have to have the groups opposite one another. Now, as far as
So Professor, if they're not 180, then it's not going to happen.
right, if they can't rotate and get to 180, then it's not going to happen. That's exactly right.
Okay, thank you.
Yeah. So if I had, let's do an example. Let's take a look at something like that. Let's say I had a cyclohexane, and I had my H, which is up like that, and I have my leaving group like that. They aren't 180. If I do a chair flip, let's do a chair flip and see if maybe they'll be 180 in my chair flip. So the H was axial, the H goes equatorial. So there's my H. And my leaving group was equatorial. Now my leaving group is axial. They're still not 180. So these guys are not 180. There would be no reaction in an E2. Just won't work. So you have to be able to rotate or something to get them 180 degrees apart. The E1 doesn't have that issue. So highlight that. The E1 mechanism does not have that requirement. And that's because the leaving group is already gone when you remove the hydrogen. So there's no point talking about them being anti-periplanar because the leaving groups left the picture. And this shows an example of that. There is no leaving group here. It has left already. We have a carbocation. I can pull any H off that I want to. I could get the one that they're showing. I could get that one. I could get that one. Doesn't matter because I don't have to push out a leaving group. It's already gone. Okay, now let's look at some examples of where that becomes a factor. And then we'll, I think after the end of this slide, we'll go ahead and do that homework. Look at that. So for E2, you have to get the leaving group and the H, anti-coplanar. So what I've got in this particular top molecule, now that branched alkane, is I have my bromine coming towards me, and then I have a methyl coming towards me right next to it. And that means the hydrogen is going away. And so when I do the Newman projection of that, you can see that I have the bromine and the hydrogen opposite. The bromine's coming at me, the hydrogen's going away. So this guy is set up for the reaction to happen. They are towards me, away from me. As this thing exists, these guys are anti-coplanar. And so when I get my double bond, I'll have the methyl at the end down, just like it was here, it's down. My double bond is now in between. Then the other methyl is down, just like that methyl's down. And so the methyls didn't rotate, and so they stay exactly where they were. Now, let's take a look at what would happen if this was different. What if it looked like this? What if I had my bromine forward and I had my CH3 back? Like that. What if it was like that and then the H was forward?
You would need to switch them.
Yeah, I can't do it now. So there, as it stands, just like I've drawn it, these guys are not anti-periplanar. Co and peri are, by the way, they mean the same thing. And so like it is, it's not going to go. So what I'm going to have to do is rotate something. So let's go ahead and let's just rotate right there and redraw this on the rotated scale. So I've got my methyl up, then I come to the bromine, which is going to be back. Let's draw it like this. Okay, so we have the methyl up. My CH3 is still back. I think I got my isopropyl messed up. We'll fix that in a minute. H is still forward. I left that one carbon the same. The methyl's up, and now the bromine is to the back. So I just spun it around, the bromine's back, the methyl's up, and then I have an isopropyl sticking out like that. Now they're anticoplanar. And when I hit it with a base, the base attacks the H, electrons come down, kick out the bromine, and my molecule will be a little different. Methyl up, double bond, methyl down, isopropyl. So now my methyls are on opposite sides because I had to rotate one around to get it anti-periplanar. Okay. This example, I think we'll stop here and do the worksheet. This example right here with the rings, we'll take up with that one next time. It's a little bit complicated and I don't want to spend a ton of time right now. I want to do that homework. All right. So you guys take out your homework 3 and let's go ahead and do it real fast. Okay, we're going to do S if it's a substitution, E if it's an elimination, and R if there's a rearrangement. So on the first one, we are creating a double bond. I've also got a base. This is O minus. It's a weird looking base, but it's a base. It's called tert-butoxide, and we'll learn about that next time. So this is an E, and I don't see a rearrangement. The next one, I created a double bond, so it's E. Did it rearrange?
Yes.
Yes.
Yeah.
Yes.
Three membered went to 4, so there's a rearrangement. This next one, it almost looks like an elimination if you weren't paying close attention, but I have a double bond, double bond. I didn't create a new one. It just moved around. So what really happened that's different is the OH turned into a BR. So it is a substitution and the double bond moved. So it had to be a rearrangement.
Professor, do we all have different worksheets with different molecules?
I don't think so. Is this one a weird one? Does it look different to you?
No, this one looks
Yeah.
the same to me.
I have a different one. I think I went into the one where the submission link is, and I pressed that attachment. And so it's like the same setup, it's just different molecules.
Oh, really? How about these lower ones are different too?
I believe so.
what I'll do is, that's weird, but I'll take a look and I'll put up the answers to the other one. And so you guys
Okay.
can just take a look at that, okay?
Sounds good.
All right. Okay, this next one, I'm taking a bromine, turning it into a CN, good nucleophile, acetone. That's a substitution. It's also an SN2. All right, here we go. Going through these molecules. The substrate on A is tertiary. And so I know that it can't be SN2 because it's tertiary. And I know it's a substitution because Br turned into I. So it has to be an SN1 reaction. All right, how about the next one? Is the next one a substitution or an elimination?
It's a substitution.
Yeah, the double bond didn't get created, so it's a substitution. So I know it's an SN. 1 or 2?
I said 2, but I think it gets 1 now with the OH.
Yep, it's 1. You've got a couple things that are your clue. First is you have a poor nucleophile. And the second is the double bond moved. That's a rearrangement. Those are only seen when you have a carbocation. So if you see a rearrangement, it went through a carbocation.
Since we didn't go over the SN1 reactions to today, like, are we gonna get knocked down points for that if we didn't write, if we got it wrong, like, if we wrote SN2 instead of SN1?
You'll end up, each one of these is the S part, S versus E is like half of the points. So you can tell based on just, we went over the poor nucleophiles being SN1, and that could be your first clue. And so you'll lose a small amount of points, but it's not major at all.
Yeah, I just feel like we didn't really go into that level of detail. I know we talked about the nucleophile a little bit, but I just feel like today was really good on actually, like, I now know what an SN1 is instead
We'll
of
see how it
before.
goes. I'll take
Okay.
up those on a person by person basis.
Okay.
Okay, so this next one, we have secondary, which could do either one. We have a good nucleophile. And my solvent is aprotic. So this is SN2. What's another clue that it was an SN2?
Version of stereochemistry?
You got it. Yep, right here. What was going forward is now going back. So is an inversion. All right. What kind of reaction was the next one? It was an elimination. Yep, so E, that's all you guys had right. What kind of elimination? Can you guess?
E1.
E1.
Arrangement.
Yep, how'd you know? You saw rearrangement and the base is weak. Weak base and a rearrangement. So it ended up being an E1. What's the next kind of reaction? Is it a substitution or elimination?
Hi, Sean.
How about elimination? E1 or E2?
E2.
You got it, E2. And you can tell that because you have a strong base. Okay. Next one, substitution or elimination?
Substitution.
Substitution, so it's an SN 1 or 2.
One.
1. Yep. Poor nucleophile. All right. Now here's something weird for you. And someone asked this when we had office hours today. SN1, but the substrate here, this is a primary substrate, right? And we learned that primary carbocations are generally not very stable and don't really form very well. But this one did. What's the difference?
Resonance stabilized?
You got it. Yep. There's a double bond. There's a plus. This is allylic. And so it's resonance stabilized. And so it forms allylic carbocations are about as stable as a tertiary because of that resonance. Okay, this next one for you guys, all you had to answer was E. You create a double bond. Now, can you tell me what kind of E it is now? It's a 1 or a 2?
E1.
1.
Looking at 1. I'm going to redraw this thing at the top. It's drawn very oddly. It is this. It's O minus with a tert butyl group. Does that help? It's basically the conjugate base of an alcohol, so it's an RO minus. What kind of a base is RO minus? Let's take a look back. Go to right here. We go back and look at our bases. There's an alcohol right there. It's a CH3, but you could make this an ethyl if you wanted to. You could make it an isopropyl. Any conjugate base of an alcohol, you could make it a tert butyl if you wanted to. So this guy is a strong base. And it turns out this is an E2 because of that strong base. All right. On H, elimination or substitution?
Elimination.
Elimination. So that's an E. And we haven't covered this mechanism yet, but we're going to see that it is an E1. It goes by an E1 mechanism. And we'll see this one when we come back on Monday. We start
Like, is
looking at all the. Go ahead.
Is that because alkyl shift, or it's an alkyl shift, right? Like a hydride shift, but an alkyl shift?
Yeah, exactly. That's it. So you can see that, yeah, that's a good clue, even if you don't know the mechanism. You see here that you have 3 CH3s, and here you have 2. So 1 moved. So it's an E1. And we'll take a look at the mechanism with a few rearrangements on Monday. That's kind of under the rearrangement area that we're going to do in lab. All right, this next one, substitution or elimination?
Substitution.
It's a substitution. Okay. SN1, SN2.
SN2.
SN2. What makes you say that?
A strong base.
You have a strong base. That's that OR minus. So this is a good base. And remember, good bases are good nucleophiles. So you've got a good nucleophile. The real clue is right here. It's a methyl group. And methyl groups are great SN2 substrates. And you will not see a methyl group form a carbocation. They just don't happen. And so it's an SN2. So I'll take a look and see what that other homework was and pop up key for it for you guys that downloaded that one. And then next time we'll kind of do special topics. We'll do a little more elimination, talk a little bit more about that, do some practice examples, and then we'll do a lot of rearrangements in lab. All right, that's all I got. So I'll see some of you at 7 o'clock and we'll do the NMR quiz in lab for, it's an hour and 15 minutes. And then after that, we'll talk about 10B.
many questions was it?
How many questions? 20, I think is what it was.
Was it something?
Do we need to
Yeah, it's fine.
download anything? I know we have those couple problems that we need to like upload. Is there a link to something that we need to download prior to the
You know-
quiz or?
No, you don't need to. You can just, you'll have the questions on the screen and then you can just work them out on a piece of paper if you want.
Okay, I just want to make sure I have everything prepared because I'm
Yep.
going to try this uploading thing for the first time. So,
If it doesn't upload, and there were, I think, 2 or 3 people that had some issues, you need to email me the files directly after the exam. Don't hang on to them for hours.
okay, yeah, thank you.
Okay.
What time is it starting at?
It'll start at, let's start at 7:05. That'll give you guys a time to rest a little bit more than 8 minutes. So I'll open up the quiz at 7:05 sharp, and I'll be monitoring email as well as you guys do it. So if you have any issues, you can email me because there were some issues today with some question missing. So
Professor?
Huh?
I received your email like an hour ago, but then I sent my my exams like right after it. So can you double check? It's from another account. So maybe that's why. I checked it over and over again.
I did get it. Can you send me a screenshot as well of where it was sent?
Yeah, I'll send it to you.
Yeah, send that to me. And
Yeah.
yeah, I do see that this one came through, but screenshot me where you sent it right after the exam.
Okay, I'll do that. And I'll
Okay,
send it
all right.
to you. Thank you.
Okay. All right.
We start
I'll talk to you guys.
8:35.
So we'll start, I think the question was, will we start lab right after? And we will. So we'll start the test at 7:05. It goes an hour and 15. So what is that, 7:20? No, 8:20. So we'll start talking about 10B at about 8:30.
Okay, sounds good. Thank you.
Okay,